because some maybe from Europe. Yeah, so welcome to this CS STXM data analysis webinar. So yeah, the motivation for this webinar, I think two motivations. The first is to help users to be more productive and on their data analysis publication preparation. The other is when user come to STXM Beamlab, more efficient to use their beam time and prompt analysis of their data during beam time will give a quick feedback and on some of preparation materials. So with that, I think that we have been thinking about this kind of webinar for a long time. Eventually, I think this Xiaodang, our manager Chitra, she supported this idea very much, and Yinshan put the arrangement, organize this webinar, and myself. And today, my name is Jian Wang, I'm the STXM scientist, and the other scientist, Jay Dines. Today, we two will be the training facilitators. Okay, so I think for the data to gain the data analysis capability is a very long-term process. So you need more practice, and with time going on, so you gain more experience, and you may also have some experience or skills to share with each other. So in the future, feel free to share what you learned, tips or skills, so that everybody in the STXM community can benefit from each other. Okay. So yeah, let's get started. So okay, how to page down?
Use the arrows.
It's slow. It's slow. So yeah. So for today, so we basically we have two sessions, about 1 hour each session. So I will be leading the first session. So the first session will be just some basic skills, basic operation of the Axis 2000 software. The second session will be covered by Jay. He will be talking about the more advanced analysis of STXM data analysis, like a PCA, GUI, Mantis, or ImageJ plugins. So for the software, for today's training session, you need Axis 2000, and you need an IDF virtual machine, which is a platform for the software, and other IDF-based application like a stack analyze, the PCA GUI. So I think you will be able to get this all free software. So
and they are on Access too.
Yeah, and Python-based Mantis and other software like ImageJ, plugin MATLAB. Some people like MATLAB for their image processing. It's also okay. So also for the spectroscopy analysis, you can use other software like Athena, like other professional plotting software to be fine. So to get the Access 2000 software, it's from Alan Hitchcock Group website. So in the website, you will be able to download the software package. It's actually application. You need to download the IDEA virtual machine first to get installed IDEA virtual machine. Then you will unzip the Access 2000 in the specific folder, dear path. So okay, I think there's some issue with anyway. It looks like We're
not moving.
That's slow. Okay, it's slow. Yeah. Okay. It's a little bit slow. So maybe I turn. Yeah, so just keep in mind the installation of Access 2000 software is very specific location. Is at a C drive root directory, and the name is very specific, Access 2000. And the executable file is Access 2000.sav. This is the executable file for the IDL language. So if you want to, sometimes you need to go back to the old versions. There's also available the older versions and the online tutorials from the website. So, so if you are using Linux or other operating system, so the installation may be a little bit challenging. So in case you have problems, you can email Alan Hitchcock for any errors or bugs for the software, for the installation, or even for the operation of the software. So here, there's also a menu for the Access 2000. It's a PDF menu. Basically, it's more like a function as a description for all the functions. So today, we will be using. You can refer to the manual later during your data analysis by your own. So if you have questions, you can also refer to the Access 2000. Today we'll be using the software for a little bit of demonstration. So the right side shows the GUI, of the Access 2000. So it's arranged by some buttons, panels. So the GUI.
Whoever just came on, you need to turn your sound off. Thanks.
So the GUI, we will cover this GUI later. You will see many screenshots during the presentation. So basically, there are some important GUI in the top, arranged by the functions, data set formats, and some utilities and displays. And other for the display GUI, there are limits you can change, XY dimensions, intensities, and they all can be modified on the GUI. And the intensity bar is very important. You can see the intensity of each image. Oh, let's move on. So let's first look at the STXM images. So to read a STXM image, you always start from the read. The read is there's a few options. You can read like a STF, which is standard file for STXM, or you can also read the new data format for across STXM, like a STXM Nexus file. You can also read team and read other images, graphic image, or the same image or from other synchrotron spectral images stack. So this is a read. So that read is actually for raw data or for some particular format data. So that's a read. So for the ambient STXM data format, typical for each data set is comprised of two files. The first file is called a header file. The header file is actually has all the information for the during the acquisition of the image is basically microscope parameter settings. So the other file is called a .xim file. Is the image file is basically a 2D array. So it basically is each pixel the transmission intensity, which basically counts at each pixel. That's integers up to a few thousand, depending on the transmission. So the other format is the spectrum file .xsp. So these are just a single column or multiple column, just like a very standard TXT spectrum files. So one good naming system for these files are arranged by microscope designation, like A means ambient STXM, C means cross STXM, then arranged by these dates of the data acquired, and then followed by the sequence number, the 3-digit sequence number. So each day up to 999. So actually we never got more than 999 data files on a single day. Okay, then the reader STXM ambient images. So when you open the reader, you should be able the SDF. You should be able to see this small widget. In this widget, you can do some change. I just highlighted this important input box. Sometimes you need to consider to change, like a normalization. Sometimes you don't have a ring current record in the data set, then you do the normalization will fail. So and the other thing that ring normalization current number, so you can change. This is just a default number of 500. So it depends on how accurately you want the intensity to be meaningful. Then you should pay attention to the normalization current. And these are the other functions you can read a single image. This single image basically is disabled because this is just single image. You want to be able to see the map and the image and the regions, counters. So for operational single image on the Access 2000 display panel, you have 3 clicks. The first click you can select a point on image, and the second click you will click another point. Then we'll do an automatic calculation between the 2 points. Will be dx, dy, dr, dz, and finally a third click it will be cancel, remove all the previous selections clicks. So you can also do a little bit treatment of the image, like a cut, zooming. These are the zooming cuts. So you can just zoom a particular region. For this case, a single region you can cut, and yeah. So the next one is a filter. Sometimes you want to improve the image quality, you can do a little bit smooth, a few points average, or the median value average. So this is called a filter. If you have modulation, sometimes you have modulation in your image, like those stripes or lines in your image. You can do a Fourier transform cleaning, which is this one. So these functions are very straightforward. You just click and follow the instruction prompts from the software. So now we for images. So now you see the column for the images. For each kind of data set, there is a specific column for the process of the images. So the images processing is very important. You can see I highlight many functions. So these functions, normally you will use them to do some image process, such as convert to OD from transmission image, convert to optic density image. You click convert to OD. You can add average image together. Clipper image, clipper signal is also very important. You can select a threshold in your image. Just select the 2-point threshold. Just highlight the intensity within 2 limits. The gain, you can change the image intensity. General mask, you can basically turn the image into a mask. Mask basically have the intensity only 0 and 1. So with the mask, you can do a lot of operations. Then you can also do multiple buffers, image times image, 2D array by 2D array time, and you can do power, you can ratio, and these are the useful functions. So the other one is a display. A display not only for images, also for spectrum is also using display. For display, you can change the limits on the X, Y, Z limits to change the contrast, change the size. You can also do the changing, modify the color of your image. Basically, is a modify image colors. Scale by position, the thumbnails to have a multiple image displayed together. So these are the display. And the next one is utilities. The last button. So the utility has some important features. for images, the utility, you can use the utilities to change the pixel size, mesh, it's called mesh size, and also change the label of your image, the labeling information like energy, dwell time, and you can also access to a printer, it's called print, just for the utilities. So we will be to see the utilities again later. So finally, when you have an image, do a little bit of processing. You want to save the image, then you move to this column. You call it write. You can write access 2000 image for access 2000 image format. The access format is a binary format. So you can also write the image into graphics format. There are 4 standard graphics format like TIFF format, PNG format, JPEG format, something like that. And you can also write the image into the TXT image, text image, basically just writing the image into a 2D array of data. And there are also other formats like NSLS image format is binary format for compiling stacks. So now we move on to the spectra. So spectra, so read spectra, still using the read button. The first button is a standard file. So for the spectra reading, you pay attention to the region. You can select only one single region to read, or you can select all region. When you click all region, all the columns of spectrum will be loaded onto different buffers on the right. You see the 5 spectrum in read into the buffers. So again, so you can do multiple clicks on the panel to see the difference between the two selections on the spectrum panel. So this particular case is a common nanotube, the nitrogen doped common nanotube. So these are the measurements. This shows the screenshot of the STXM measurement of the 5 spectrum. So number 5 is I0, number 1, 2, 3, 4 on sample. So these are basically the measurement have I0 and I. So again, like image processing, you can do zoom. You can do a cursor zoom or numeric zoom. Basically, you can limit X, Y limits, Y intensity limits, and the cursor cutting. You can put your cursor onto the panel of the spectrum and just will be trimmed to the selection region for zooming. Filter, spectral filter is just like an image filter. You can do a little bit of filtering, like smoothing. Normally we do a multiple points, 2 or 3 points averaging to make the spectrum slightly smooth. And the other algorithm is the median smoothing. You can the spectrum filter. So the spectrum processing. So you another column.
So how do you just go to the link and click it? Right?
No, this is software. This is app. Yeah, you can just click the link.
Yeah. Okay.
So this
Whoever just signed on, can you turn off your microphone?
Yeah.
Okay. No problem. So for the column of the spectra, there are many.
But you go back to Shanghai for the summer?
Oh yeah. I find my mouse is difficult to. Yeah. Okay. So yeah, I sit like this.
Doesn't matter. I can see.
So for the spectrum processing, So the column, I highlighted these very important and mostly used functions, like calibration is very important. You can calibrate X and Y of your spectrum. You can do converter spectrum, transmission spectrum to a absorption spectrum. You can also do curve fitting. We will using this later. And you can delete the spectrum bad data points on spectrum. So just click 2 clicks, you can delete a region, single point on the spectrum. Some like a glitches you can remove by delete. And again, you can change the spectrum intensity. You can also linear background the baseline to get the multiply spectrum power, the other similar to the image processing. So one important is to convert to optical density. So I0 is 5. Any other spectrum you can normalize to the I0. You get the positive spectrum, which is optic density. This is nitrogen spectrum, high resolution nitrogen spectrum. So this is the optic density spectrum. So for the display, so one important function for spectrum display is overplot. In many cases, you will be using this to compare multiple spectrum together. You can do a no rescale their Y intensity or rescale their Y intensity, or just set a different window to display of those spectrum. So overplot is a very useful function for display multiple spectrum together. So that's the display. Right, finally, when you have your spectrum convert to optic density, do some cleaning, do some calibration of energy, then you can write spectrum. Typical format for writing a spectrum is axis format, is not binary. This is TXT format, and you can also write in the XAS format. The XAS format is compatible with some other software like PCA GUI and Stack Analyze. We move on to the next type of a data set is line scans. So the line scans. So first, you need to understand the line scans format. So the line scans is the X direction is the energy direction, the energy of the scan. The Y is actually the physical length of the line acquired during experiment. So when you see some black region, dark region, that means the sample region, which has a lower transmission. The brighter region typically is an empty region without a sample. So that will be used for normalization.
Hi, John, can you hear me?
Yeah.
Yeah, so I just wanted to let you know that the screen that we're seeing here on the webinar, it hasn't changed from the web page that shows Axis 2000 on Hitchcock's group. So none of the slides that you've been discussing have shown on the screen. Now, I'm following along separately on the PDF file, but I just wanted to let you know that the rest of the users can't see what you're looking at.
Oh, I see. That's basically, that's right. Okay. We are sharing a different one. Actually, we should share this one. Then screen 1 and 2. Okay, I see. So because we are using expanded screen, so
there we go.
Yeah, this one.
Yes, that's better.
Yeah, that's so this is actually our first time to do this kind of. So we
no worries.
Yeah, well, I think in the future it will be better. So.
Okay,
So basically, we have 2 screens. The one is my laptop. The other one is a bigger screen extended screen. So
So now you can see it?
Yes. Yeah. Now we can see it.
Yeah. So we are doing the line scan data reading. So line scan, just this note, this is kind of a line scan. The line scan is called line scan image. Basically, it's an image, but the dimension is different. The X dimension is the energy. The Y dimension is the length, the physical length of the line. So again, you can do multiple clicks on the spectral image, but that's not much useful information. So the next slide is to do a quick analysis of a line scans. The analysis of line scans, you need to find the I0 region, I3 region. So do add lines, normalize to I0, then you can convert this image into the optic density image. Then you select the lines on the region, do an average between the two lines, you get an optic density spectrum. So these are, you can practice later. So finally, I think I will mostly cover the important part is STACS. So STACS is a sequence of images at different photon energies. So these are transmission raw data. So typically process is we do alignment, we do a conversion, the transmission stack into the optic density. Then we can select, manually select the spectrum from the sample region to get the spectrum. You can also do PCA analysis. Jay will be talking about the PCA analysis. I will be talking about the fitting, using the spectrum, internal spectrum. You can do some scaling of the spectrum to get a linear reference spectrum to fit linear combination fit the spectrum to get the quantitative information of the stack from the stack. So before moving on to the analysis, a good naming system for the files is very important. So you won't be lost during data analysis. So we strongly recommend you to follow some kind of naming rules on slide 31. So yeah, that will be much organized during data analysis. So stacks. So first is to read the stack. The reading of a stack is more like a compiling the stack into a NCV binary format, into a movie format. So after compiling, so they will generate the software will generate two files. The one file is called a date file, which is information of the stack. Basically, just the pixel size, pixel numbers, and the physical size and the photon energy for each image. The other file is a .ncb file is a binary stack data file. It's just a movie, only have the intensity images. So pay attention to ring normalization current, and sometimes the image is missing the ring current information. Make sure uncheck the normalization to ring current. Stacks, there's a very specific column in the software for the stacks. For the stacks, typically the first one is very important to analyze. So we will be using a stack process and other Jacobson stack analyze or Zimba for some demonstration later, maybe if we have time. And for stack, also the other important like change the size, mesh of the stack, and also do fitting and math and do some statistical analysis. These are some useful functions for stacks. So when you click the stack process, we are into this widget. It's a window. So it's called Access 2000 stack process. So this widget is divided into a few sections like display control, data manipulation, output menu, and these are the interactive display of image. So basically, I highlighted these functions very useful. Like you can change the contrast of the image by gamma, and you can limit the stack range by the minimum maximum energy range. You can also select a region for select the region for I0. If you have I0 region, you can use load the region of interest file. You can do the subtraction between any two images in your stack, which is causing map. You can remove some bad images. Finally, you can convert the image into object density. Other important function like average the whole stack. You give your noise removed image, and you can calibrate energy scale over here. And also you can do some mathematical operation of the stack by process. Here you can do the whole stack can be multiplied by a spectrum, by a constant, by even a mask. Finally, is the output the path. Make sure the data saving path has no space, and give a file name for the stack of images, and make sure you enter. You will be activating the saving buttons. So for the first thing is to the alignment of the stacks. I would strongly recommend using the stack analyze, which was written by Chris Jacobson group when he was at Stony Brook University. So this is a very good software. So here, read the stack file. You can read the NCB format, and yeah, when we compile the data into NCB format, you can read the stack from here. Read the stack NCB format. You can change the size of the display by zoom. Then you can do some align stack or saving the stack. I think there are other functions. You can save the spectrum into the image or into a movie, like a GIF image movie. These are the some functions are not available. They are only for the licensed version of IDF. So the IDF virtual machine doesn't support MPG for movie format. So they only support the GIF movie. So so again, the align stack is always the first step. You do align stack, so then you will be into this window, and so you will select some. Normally these are some default settings are good enough, like without edge enhancement, and these are default size shifting, limiting shifting. So they are good. So then you just press auto alignment. Yeah. So they are very straightforward. So after alignment, you can select a region for I0. So basically, you click add select I0 from histogram. So this button. So you will be into this window. From this window, you can click and drag to select a peak for the I0. Then you see this red region is selected for I0. And then you can also manually select a sample region. There's a green region. Then you can do a optic density or flux transmission conversion over here. Then you will see the displayed. So after the other is Zimba. Zimba is also integrated actually part for the Access 2000. Is developed by Zimba. That's the person name. Okay, so these are the paths for this software. For this software, they have a capability to compile some single image into a stack, but normally we don't need to compile. So already compiled, you just load the NCB file from the directory, data directory. When you see all the images loaded, you click a list is complete over here. Then you are moving to the alignment. The alignment procedure is exactly the same like the the stack analyze procedure, the same, so I don't need to talk about this. Finally, after the alignment, you go to the called Zimba stack spectra, the Z stack spectra. So in this window, you will be able to select I0, you will be able to select I region and convert the spectrum into optic density, and you can save the manually selective multiple spectrum, save them. So these are the saving functions. You can also save the selection mask as a .I region of interest file, ROI file. So there are some general guidelines what you need to do for the. So first, I think it's good to do like a save optic density stack. So only the Axis 2000 stack process has a function like a save optic density stack. So that means that you need to click the optic, convert the optic density to over here, to click this to optic density, then give a name, and finally you save the stack over here. So after the stack is saved into an optic density format, you open the stack again, basically follow the procedure. You will be open the stack again. Then you can use the I region, select a sample region. Then, because this one, the stack process doesn't have multiple selection. All the multiple selection will be averaged into one output spectrum. So only the Zimba spectra has the capability to save multiple spectrum. But this one, multiple selection will be averaged into one spectrum file. So anyways, so you can select a region. So for example, we select this sample region. This region is the carbon nanotube. Inside the carbon nanotube, there are some trapped nitrogen gas. So when we select this region, you see a nitrogen absorption spectrum. There's a nitrogen. So then you can save the spectrum, give a name, and save spectrum. So then we can select another region on the stack. So this is just without a nitrogen gas, is just the nitrogen doped carbon nanotube framework, carbon nanotube wall structure. So select this region, get this spectrum. So basically you have two spectrum. One is the gas in the tube. The other one is just purely for the tube, and save the spectrum. So the other good thing is, as I said, is the average stack. When you have an average stack, the average all the image of the stack give you a good high quality image. From that image, you can do a further treatment to convert that image into mask. This is very useful. How to get a mask? Just follow the procedure. You get a mask. So this is a mask selection window. You can slide the lower limit and higher limit to get the best select. The red region is the selected region. So this is the selected region so this is a mask. So you see this is a mask. And loading this mask, you can buy. When you open the stack, you load the mask by region of interest file, and loading the mask will give you the mask region, the average spectrum. So you see, it's a mixture of nitrogen gas and nitrogen doped carbon nanotube structure. So this is a mixture as well, and you can save this spectrum. So the other good thing for mask is you can do a multiplication the mask with the stack to remove all the background noise. So this by the procedure times the mask, and you only have the masked region stack left. And from this region you can select a spectrum. So this is to help you get a high contrast masked stack. sometimes you need to combine two stacks together. So nowadays our STXM is finely tuned. You can do multiple stacks without too much problem. So the misalignment and the focusing is way improved. So you can do so typically we can do from carbon edge to iron edge 4 or 5 elements together for a big stack like more than 400 or 500 images. But in the early days we acquire stacks at a different element edge. In this case, this data set include a carbon 1s stack and nitrogen 1s stack. To join these two stacks together, you follow the procedure. So sometimes these two stacks can be quite different in physical size and also in the pixel size. So the procedure, the general guidelines, you need to have one stack as a reference. So typically use the low resolution, smaller physical size as a reference. So the other one, like a nitrogen 1s stack, you do modification to match the carbon 1s. So what we do is for nitrogen 1s stack, the physical size is slightly bigger. So we need to trim out the X and the Y by particular pixel numbers. So to trim the stack, basically to resave the stack by changing the columns or rows of the stack. So there's a procedure over here. So trim the stack of a nitrogen stack into smaller size, and then you do a rematch the stack size pixel number to match exactly same pixel numbers for the carbon stack. Then you can append the two stacks together. So appending procedure is over here. Finally, you can check the appended stacks together. Then this carbon 1s, you see a selection of the sample region. You have carbon 1s and nitrogen 1s spectrum show. The other one is important is to do some kind of elemental mapping. So elemental mapping is basically just like an on-off mapping. Is basically a pre-edge image, and you get another on image on the peak image. Subtraction of the two images give you the absorption difference at the two energies. So in this case, typically what we do is we first limit the energy range for a stack. So first you want to get a background image. If you want to get a background image, you limit the energy range. So in this case, we limit the energy to 280 to 282 for the carbon 1s pre-edge. You limit the energy to pre-edge, and you take the average stack. Then you give your pre-edge image. Then you save that image as a pre-edge. Then you do another change of the energy range to the peak energy. Then you average the stack again. You save the peak image. The two images you can use Access 2000 to do a subtraction between them. Finally, you get the map. This is called elemental map or function function group map. So similarly, you can do the nitrogen pi star mapping by the energy average of the images between the energy ranges. So then finally, you can do a composite image. So when you have the spectrum, you can do a fit, stack fit. So this is called Access 2000 stacks and maps. So as I showed before, you can manually select a nitrogen spectrum on your stack. You can also select a tube structure spectrum on the from the stack. So this is a tube, this is a nitrogen. So then you do a mapping, which is under the stacks maps. Stack fit and SVD. The difference between stack fit and SVD is stack fit has an additional constant. So it's very straightforward. Follow the procedure. Finally, will generate the fitted results. So the buffer number 4 is the component 0. Basically, component 0 is nitrogen distribution image will be placed over here. The tube structure image will be placed over here. So the next one is to do some image contrast enhancement. So for the nitrogen, you can do clip some signal, limit the range, only have the best intensity data left in the image. After the cleaning, you can place this image back into buffer number 1. So this one is a tube structure image. You can do some cleaning background, then place over here. So and if you want a third color, because these are 2 components, you need to pick any of the image times intensity 0. So to change this image into intensity 0 and place this image into buffer number 3. So you have a 2 component image and background 0. So then you do display RGB composite, red as nitrogen, green as a structure, and blue as a blank image. Finally, you get a color composite image over here. So utilizing the internal spectrum, you are able to differentiate the species and display this is a color composite image. The color composite image is a TIFF format, can be analyzed by any other software. So you can also do the spectrum fitting. Remember, we have a mask to select all the spectrum from the sample region. So all the spectrum from the sample region, just like this spectrum is the average, and it can be fitted by the 2 components that we manually selected. So in this curve fitting is in spectra, curve fit, follow the instructions, is also the linear regression and SVD, same idea like a stack fitting, and follow the instruction. Finally, you will see the fitting result in the buffers. So the first buffer still the original, the whole average of the spectrum. Buffer number 2 is the component 0, which is the nitrogen. Component 1 is a nanotube structure. So and this is a constant. So that means the fitting there are some constant. And finally, the light green one is a fitted result. You can compare the fitted result as to the original one. You can see the fitting is very good. And there are some fitting quality parameters. You can check the fitting quality. So there's a stack fit. Finally, I just talk about the quantitation. The general quantitation is using Beer's law. The Beer's law is based on the transmission. So if this is an elemental profile, so in this case is a polymer structure. So if this has a chemical composition like a C5HAO2 have a specific density, their elemental X-ray absorption profile is just like a steps. So the idea is you need to scale your obtained spectrum to the calculated X-ray elemental profile. Then this green spectrum is meaningful, which is a single per nanometer, because the red spectrum is for 1 nanometer thickness elemental behavior. So the green one scale to the elemental behavior, you get the 1 nanometer absorption spectrum. So with this 1 nanometer absorption spectrum, we call OD1 spectrum, you can fit your stack. Then the fitted result will be quantity in terms of thickness, like a nanometer. These are just some X-ray series. What is the mass coefficient, mass absorption coefficient, F1, F2 scattering factors. So basically, we are using absorption coefficient is F2 of the scattering factor to calculate the elemental X-ray absorption. So to generate to calculate elemental X-ray absorption for particular composition. So using the utilities, using the Access 2000 utilities, calculate the XY parameters, and give a formula. In this case, we only use the carbon, the graphite. So you define the minimum energy transmission. We want to calculate current transmission and give a density for this particular. So we are using graphite as a density for this carbon, elemental carbon. Thickness 1 nanometer, finally convert to optic density. Okay, then this spectrum is 1 nanometer graphite elemental X-ray absorption profile. It's just a step. The energy range is from 200 to like 1000 eV. So with this elemental profile is pure carbon, so we can use like a carbon nanotube or graphene can be scaled to this elemental profile to get a 1 nanometer graphene, 1 nanometer carbon nanotube X-ray absorption spectrum. So the procedure is detailed over here. So this is a carbon nanotube spectrum. So finally, the idea follow the structure, follow the procedure. The idea is to scale the carbon nanotube spectrum onto the X-ray elemental absorption of carbon with the same specific density. So do the same thing for the graphene. You will get the graphene spectrum 1 nanometer. This is a graphene 1 nanometer spectrum. So finally, with 1 nanometer of a graphene spectrum, 1 nanometer of carbon nanotube spectrum, so you do the stack fitting again, follow the procedure, and finally the result is quantitative. So in this case, we have the sample has 5 nanometer of graphene in some regions, like a film region, and up to like a 50 nanometer of carbon nanotube on some tube. So this is a mixture of this is called a partly open carbon nanotube. It's called nano ribbon or open nano ribbon. So in this case, you can nicely map the graphene and carbon nanotube based on the thickness can be determined. Okay, this is a quick summary of the stack analysis. I think this is from Alan Hitchcock. So basically covered all I just mentioned. So during measurement, there's some tips for the measurement. Find the region, find the I0 region, and check the radiation damage, check the energy calibration, make sure the validation of the I0. Then the stacks, basically you follow similar, this is like a process of the stack. Just like I talked, convert to OD, alignment, Zimba, get a spectrum, finally fitting, clean, yeah, and then you will be doing some GUI, PC analysis, Mantis analysis, something like that. The last part is just a little bit about a cross-Dixon data format. So you can see that the cross-Dixon data format is quite different from the ambient Dixon. The cross-Dixon data format is everything in a single file. The file is actually binary file, is a structured file, is HDF file format. They have structured more like directory for all the information of the file, including the microscope settings parameters, and also the data. The everything, just like a HDI, just like the ambient Dixon, the data file and header file, they all integrate into a single file for the cross-Dixon data format. So there are some examples in the demonstration data. Read across Dixon image very similarly, just try to pay attention to sometimes you need the flip image, make sure you select the right correct software. So because this image is generated by Dixon, if you choose a different the other microscope from Swiss light source, you won't be able to preview the image. So make sure you select the correct microscope. Other similar like Dixon. Same thing for the point spectrum reading, preview, and you can load. For the stacks, similarly, yeah, just make sure select the correct format. From the data analysis, they are pretty much the same like Dixon. So yeah, I think just right on time, 1 hour to get a quick overview of the functions of some basic skills operation. So yeah, if you have any questions, I think we have a limited time today. So if you have questions, you can email us, or we can set up some interactive sessions individually with you by Skype or by webinar. For WebEx for if we have time, we can arrange for that kind of interactive session later. If you have questions, just simply send emails to us. Hopefully this and you can download all the data, and we'll see how much time we left when Jay finishes. That we can maybe do some kind of demonstration. Okay. So okay. Jay, you want to take over, or you want?
Yeah. Okay.
Yeah, sure. Screen stop. Yeah, it's a little bit confusion of the two screens.
That's right.
The software is.
That's the right one.
Okay. I think we need first to get this to maximize. Then we know this is a screen 1, screen 2. So this is screen 2. So make sure so that we're gonna share. So you're gonna see this one. You're gonna share. So we share this as well. So you're gonna share this. So they should be able to see, and you should be see a green box to cover the screen you are sharing. Okay. So Jay,
okay. So how do I move?
Just click. So the mouse I figure out is extended screen. So in order to get into this screen, you need to move to here. Then
right.
Okay. How come? Anyway, just.
Okay. So all the data that I'm going to be taught for my presentation is all in this aluminum stack analyze folder that I gave everyone. So I'm going to first talk about the principal component analysis and cluster analysis. How do I move here? Okay. So principal component analysis, there's two references that you need to look at. That this is what the principal component analysis is based on. The first one basically describes the principal component analysis, cluster analysis, and later they found that they had to change it, and this explains why they changed it, and I'll talk about that. So why do you want to do PCA cluster analysis? It's because the complexity of sample doesn't allow us to use the linear combination fitting where you use reference spectra of pure compounds, because we don't know what's in there, or if we want to find some new unexpected compounds. So our goal here is to identify representative spectra and produce quantitative component maps. So principal component analysis, is not going to go into it. You can go read the papers to get more, but it does this to spectra data and discards much of the noise. Goal is to describe the specimen by a set of abstract compounds. Okay, so you can go read this. Abstract components describe the main spectroscopy signatures in the data, and each signature arises from a linear combination of several chemical species, so that there is not a simple relationship between one abstract component and one particular chemical component. So this will become apparent when I show some examples. So we make a matrix, eigenvectors, eigenspectra, such. You can go read it, but I don't understand all the math myself, but it describes lots of the math. Then the cluster analysis is used to find natural groupings of spectra, which then calculates the average spectra for certain pixels and displays the thickness maps associated with these spectra. Okay. So principal component analysis. So principal component analysis, Adam actually has it in Axis. You can go through stack analysis, and it's there, or we gave it as a separate one. The reason for the separate one is, separate one you can get colored. In atoms, you can only get black and white. So you probably want to use the one that we provide separately, but if you're in a rush or something, you can use the one in Axis. Okay? The same as the stack analyze. It's also in Axis, but it's version 2.6. One we gave you is 2.7. At Beamline, we support the 2.7. The 2.6 is a little bit different, but still does the same things. So the first thing you're going to do then is read in your stack that you've already aligned and stuff. So you want to make sure it's aligned, but you don't want the optical density version, because we're going to change it to the optical density version using our XAS I0 that we generate with the stack analyze. So the first thing is to read in the file. You go here, you read in the file, comes up, and then once you read in the file, this part becomes active. Now you can read into I0. So you go to the I0. When you get the I0 up, it'll show the I0. If you're happy with it, or it doesn't matter whether you're happy or not, you have to dismiss it. So now you have a normalized stack. So we do it inside Axis, or inside this principal component analysis. Okay, so we have choices here. We can pre-process the data. You can limit the energy range. I've done this before where I had a carbon KH spectrum, and it also contained some potassium LH peaks. I didn't want to include those in the fitting, so I reduced the range. You can also go clip a subregion of your map if you only want to do that. I've never used this, and then but you can do this. An optical density filter, you can change the optical density filter. I've never used this myself neither, but you can go change that. So you can pre-process your data before you're going to go determine the number of components. Okay. So if we're going to determine the number of components, when I click on the components, it'll bring up this. It already estimates the number of components there. However, it doesn't. You just have to click on the calculate components, and it will calculate the number of components. To be able to move to the next screen, you just have to reduce the significant component to some value. So when you do the calculate components, it brings up, it shows you this graph here, and it says, do you want to save it? I normally save it because you can reload this again in the back one. It said that you could reload this again, and you wouldn't have to go through the pre-processing. So this is showing the number of the components. It's estimating there's 90 in this case. And it's showing you the eigenvalue and which one. So if you just looked at this, the first component is here. This is most significant, or not the most significant. It is most significant, but it's also in terms of number of pixels. This is also in terms of number of pixels. And so don't be deceived that, oh, there's only 1, 2, 3, 4, 5. There may be more components. And so if you looked at this window here, you can click and get the different ones ones here display the eigenspectra, and this is I'm just showing the first 5 that you go here. You can see that the first one and second one start to resemble spectra that we're used to, but these other ones don't, because they're combinations. But that doesn't mean that they're not valid here. It's doing some math here. So we can go to different components here. You can see each one here, see where their area. I generally don't move components up or down, but you could if you thought that this component down here was significant. You can move it up. So I normally click through here and see which ones are here if they're representing some kind of component. And then to get out of this, it's just dismiss. I normally don't save all these spectra, but if you left it at 90 here, you would save 90 of them. So if you are going to save here, you want to reduce this to some reasonable number, 10 or 20 or something, and save them. So to get out of this, you get to hit the dismiss button, and you will it'll go take you back to this thing here. You can click on the cluster analysis. So in cluster analysis, significant components, you're going to tell it how many there are, and I'm going to talk about how to choose the number. The sequence, how many clusters, so you change this to how many clusters you want to do. It normally finds one more than you ask it for. The scaling factor, I'm going to talk about this in a second here. And this, I'm going to talk about this distance measure. Usually it's just Euclidean. This is what they originally used in the first paper. In the second paper, they explain why the angle is better, and I will just go on that. And then you're going to get this cutoff value here. The cutoff value I will talk about here. These are things to do. And then these are other ones that you're going to, I'll look at these, the dendrogram, give you an idea of which components are significant. You can save the clusters here, but you don't want to go saving these until you're done, because you might be doing this every time you save it'll overwrite unless you change the name. So you want to go through how many significant components you want and how many spectra or clusters you want. And so here you can display all the spectra together that you get from your components. Here you can look at which ones they go. Normally the first one is due to the I0. You can see the percentage here. I couldn't get the whole screen here. You can see the component weights and clusters, what percentage they are. So this is in terms of number of pixels. And this is showing the pixels. And then this gives you the first 12 clusters, the images from so if you had 12 here, this is only showing 6. That's where the color is. If you used one in Axis, it just comes out in black and white, and you only get black and white spectra here. So if you use the one that's standalone, you will get the color. Okay. So here, why do we want to use this versus the Euclidean? Well, variations in thickness are also often classified as distinct regions, which is undesirable if we use just Euclidean. So by using the angle distance measure, then the conventional Euclidean distance measure, we can suppress the thickness variation for, and therefore the cluster data is based more clearly on the chemical speciation alone. And I don't want to go into all this, and I don't understand, but it's using the ratio of the eigenvalues instead of the difference. It uses the difference for Euclidean, and here it uses the ratio of the eigenvalues. So number of clusters to seek. I've observed that it's better to use more is better than less. So I normally try a high number such as 20, and I'll give you an example here why 20 was better than lower. Then reduce it, and then also significant amount of components. Again, try higher number than reduce to see if difference. Okay. So this is basically if I did a manual extraction of the stack, I took the different points in Zimba and get this. I can get this nice green one here where I get this is an aluminum stack where I get this great green spectra. Well, if I only use 5 significant components and 5 number, 5 clusters. I can't pull this spectra out. It's not there. There's maybe a hint of it here in this one here. But if I use 10 and 20, I can actually go pull it out. We've seen a lot of noisy spectra here too now. But I can now pull this out, which I couldn't pull it out before. This is all using scaling factor too. I'll talk about that in a sec. So you really want to use higher and then go lower, and you probably want to go to your significant components when you're in that screen and look at each one and see if there is something that stands out as a significant component. Normally you can tell whether it's just due to noise or stuff. Okay? So the scaling factor, this is just using different scaling factors. If I use scaling factor 0.2 and I'm using telling it to look for 20 clusters, it only found 10 clusters. So it reduces the number of clusters. If I use 0.3, it found 20 clusters, and 0.4 it found 21 clusters. So generally I used 0.3, but if you want to reduce the noise to get rid of some, you can tell it to do 0.2, or I've never 0.1. I can't remember what it does. Probably less. So you can reduce the number of spectra that you get. Okay. This dendrogram, it can help you interpret whether things are significantly different or not. So it's to focus on height at which two objects are joined together. I should have gave a reference, but you can go look up on the internet on how to interpret the dendrogram. But it's telling you, gives you an idea of it's this depth here of whether things are significantly different or not. So it can help you to get an idea of whether things are significant or not. Because looking at these spectra, it's hard to get an idea whether some of them are significant from each other. Okay. And this scatter plot, you can do this. I haven't found it useful in here, but I didn't. There were slide bars up here. You can change which components you look at that I've cut off here, but I haven't found it useful in here to use it in the principal component analysis. Okay. So then once you've got your clusters and you've got your spectra, I guess what I forgot to mention is that before you go to this target spectra, basically you want to whatever you used in the cluster analysis last time, that's where it's going to remember what you used. So you want to get your final values and use that, but you can. So now we can add spectra. This will be from the cluster analysis. We can actually add our own spectra too if we want. Just as long as their XAS files it's looking for. Okay, so here I've just added two. One from cluster 2 and cluster 16 that were different here. This is showing a cluster 16. You can look at the different clusters here, spectrum. You can either use the raw data, which is the green one, I think, or the fitted data spectra to do your maps. You can tell how many significant components there are, and then you can get these ones haven't been quantitative. It does allow you to go in and make them quantitative here if you want to normalize stuff. I haven't used this before, but you can go in and normalize this. You can remove the spectra if you didn't like it. Move ones up, and this is giving you some residue what's left from the fitting. And then you can go save these images as PNGs, and then you can read them into Access if you want through the graphics. Okay, and so here you're going to use. Here I've only shown two. Maybe you use a lot more to do this. This is giving the same results as the linear combination fittings, just that I found these spectra a different way instead of using pure spectra. Okay. So if we compare the spectra, this is from the PCA cluster analysis. If I use spectra 2, 5, and 6, I get this. If I use 2, 5, and 16, I get this. So it's just a number of which ones you're using. This is from the linear. If we'd done a linear combination fit, which I did before using some aluminum phosphate and gibbsite, I matched these because this spectra is more matching spectra 16, and this one's more matching spectra 2. So I get similar results as these two, so you can compare if you want between the PCA and the linear combination fitting. And okay, so you can get an idea if this is true. But this one may, if your system's really unknown, the PCA analysis may find something that you didn't find. Because that one I found manually. I was lucky to find it, but sometimes you can't always find them manually or stuff, or you can't always find them. So I recommend doing both the linear combination fitting and the PCA analysis to get an idea of what's in your sample. Okay, so Mantis PCA, say that this is Python based. It's the same as what they were using per se in the Axis. It's just that this is the next step of what they did. They just never incorporated the changes into the Axis one, into the IDL format. So now they've come to realize that you get non-negative matrix. So the problem was, if you go read these two publications, is that sometimes component maps produced by cluster analysis using the Axis version code yield some regions with slightly negative values, which are unphysical and thus represent limitations on the analysis. So what the Mantis has done now is just a Python program. So eventually I envision that Axis will move to becoming will become this Mantis. I think that's the long-term goal, that everything in Axis will be in here and it will be a Python-based program. So Mantis is just doing the same thing, and I just want to go over it briefly, and I've shown the results here. This is what we showed before, and then the Mantis. I think I've used 2 spectra, but I think one of the spectra isn't as pure as the other. That's why I'm getting a little bit more. So it's just a matter of the spectra that you choose. So I've shown the result already with the Mantis. You can get the same thing as you got linear combination fitting and the PCA analysis. Just that now this is the next step in the PCA analysis is to use this non-negative. So I haven't played enough around with the Mantis, but I think probably the Mantis is going to give you better results, or more reliable results, or more accurate results maybe than the PCA analysis. Okay. So to use Mantis, we gave you the link to Mantis to use it. It's very easy. You're just going to load that. Say when you click on it and it comes up, you're just going to load the same stack that you've aligned, and then we're just going to click over to. So we have these bars up here. Now we're just going to preset the data here. You're going to click on the I0 file. Go find it. And once you've clicked on that, this negative peak will become a positive peak. So you know that you've normalized the data. Now the data here, there's other things that you can do here if you need to line stack. These are all similar things that are in the Axis. So like I say, eventually I think everything's going to be done. Here you can line the stack, you can limit energy range and stuff. But I'm just looking at the PCA analysis today. And so then you'd go over to the PCA tab here, calculate PCA, you'd calculate here. I haven't played around here with a number of significant components, what it does, but it's doing the same thing that it did before, showing the component, and you can click on which one it is. And I don't know what the difference here is. What happens if you change the number of significant components? I think this is just what it's changing here. Okay. So then you can go. Now we go to the cluster analysis here. Calculate clusters. And again, I'm trying to find this spectrum here to use as my guide as how to do this. And I found that if you didn't use number 20 clusters, I couldn't get the spectrum. Okay? And I also found that you need to check this box to reduce the thickness effects to find this spectrum from these particles. Okay, and then I noticed that different results I noticed that you could get different results doing the calculation second time using the same settings. So I don't know if it's overwriting, remembering some settings from before. So I found that you did need to maybe do it 2 or 3 times to calculate before. And then you can save the results for spectral mapping. Again, it's just the same as the other. And then you can go into the spectral maps again. You can load spectrum. You can make a composite RGB. I'll just show that in a sec. You can remove spectrum. Again, you can see the spectrum that you've chosen. You get your maps. You can save them as PNG and open access, and you can make a composite map here too. You do the composite map here. It's the same. So it's just the target spectra. If you want to do the RGB, in this case, you just RGB, you can tell it which spectrum you want to put in. You can change the limits, the weighting, and then you can save this image. Okay, so it's just the same as before. Okay, so this is probably something different that a lot of you don't know about, is correlation analysis. So what's the problem here? So we make this RGB image, and I have aluminum 6, aluminum 4, and iron 3. Here it's pretty clear that the aluminum 4 isn't associated with the iron, and it looks like the aluminum 6 and iron are associated. So it's pretty clear in this example which ones are associated. Even here I'm seeing the little one here that's not here. So I want to do some correlation analysis to give better indication. So for some things, it may not always be clear how correlated they are and stuff. So correlation analysis, we're just going to mathematically quantify the localization of 2 variables by generating a binary map of pixels to which the signal intensifies meets certain criteria of the correlation of localization. So we're going to do something here. For our case, we're going to use the component maps that we've generated, and we use scatter plots, and I'll show this in a sec, or TD histograms used to visualize the relationship between 2 variables. And there's debate on whether to use Pearson's coefficients or Mandarin's coefficient. If you go look at this reference here, Pearson's is the one to use, and that's what we calculate, and that's what the co-localization programs are calculated as Pearson's, though there is one that calculates Mandarin's, but Pearson coefficient, it takes into account the intensity, not just the location. So accept it to be more representative of the co-localization of the correlation of the co-localization. So you can go read this paper to understand why people think this is better than Mandarin's coefficient. Okay. So correlation J, I use image J. I think you could even use axis 2008 if you wanted to plot the scatter things, but I use image J. And image J, it's been around for a long time. It's basically was used for confocal images. It's by these National Institute of Health. You can go there. They have a lot of plugins available there that you can go look in for, even for doing alignment and stuff. There's hundreds of them, but you can go look and see. I used to use this one here now, MBF, and I've given the link still, or image J. The disadvantage of these ones was when you saved your images, I actually had to go pre-process the images again, because when I saved the images as TIFF, these ones recognize the whole TIFF file, so all the header and everything as the image. So you had to actually go cut out the image. When I use this Fuji package for the image J, it understands where the image is and where the header is, and so I didn't have to do any further manipulation. So it saves a lot of time. But you can go find these anywhere you want, and there's other packages too that you can use the image J. Okay. So I'm using the scatter J, but and I should have put it on here, but correlation analysis, I'm using scatter J. It's the same as the co-localization analysis that they have in the program already. The difference is that it doesn't allow you to select an area. It only does it for the whole image. This scatter J allows us to go in and select different areas to look at the correlation of different areas of pixels. And that's why I'm using scatter J. But you can use the, if you just want a Pearson coefficient, you don't have to go through this. You can just use the co-localization. And so the plugins are these two. This one is the one I use. I think this one's for using it for stacks. I played around with it once, but I never really used it. But these you just kind of go, I gave them to you in the file, but you can just go put these into the plugin folder of your image J, and then restart it, and it will come up. So it's the stack mapping that's the advantage of using the scatter J, where I can go select an area here, and I'm just going to do that. So the first thing you want to do is loading the file. So did I have that in the back here? You want to load in your file the first time. I think did I not say that? Okay, so you're just going to browse to your file. And I use TIFF files. You can save them in Access, and I save them as data. How can I go back on that? I think how do I go back?
Yeah.
Maybe I didn't say here. I thought I said here. This is just opening scatter J. I think I'm going to talk about scatters. Yeah, this is just scatter J. You can open scatter J. You just go into plugins and go down, scroll down to scatter J and open it. It should appear there. You can have, I didn't show here, but you can go into this analyze, and there'll be a co-localization program, which is scatter J is using. You can just go into it and use the co-localization. It'll show you the scatter maps, the plot, and you can just use that co-localization if you just want Pearson's coefficient. I don't know if it might even give you the Mandarin's coefficients too, but you just want to go into plugins and it's there. So the first thing you have to do is open the files, and I use TIFF files. And from Access, you can say the XASB files as TIFF files, write graphics and TIFF, and I use the data. Note that you need to unclick the scale bar button on Access, otherwise the scale bar will become part of the TIFF image. So you need to. So when you load the file, if you see the scale bar, you know that you need to go back and unclick it. You shouldn't see the scale bar. Okay. Okay. So I'm going to talk about this. So the first thing we're going to do is we're going to create the stack plot. Select the files. So these ones I've already loaded. This is aluminum 6 coordinate, and this is iron 3 coordinate. I've loaded them, and it's basically you're just going to click on statistics when you're out there. So create, you've selected the ones you want, and this window's going to pop up. I normally show the results, draw the line, and then show the Pearson's coefficient. You can look around at these ones here. If you notice here that this is shown as 256, so it's converted, whatever values that you had for your images is converted to this 256 scale. In the scatter J, you can't change this, and I'll show you just in a sec here, but here we're getting Pearson's coefficient, and you get the slope of the line, the y-intercept, and the mean square here. So we can see that iron 3 and aluminum 6, it looks like it's coordinated 0.88, so it's pretty good. The iron 3 and the aluminum 4 is negatively correlated, so there's no correlation here between the two. Now, if you want to change these values to their real values, you can do that here. Oh, I'll talk about that, how it'll be in the next slide. So this is the advantage of using scatter J. You can use these paintbrush tools. And you can go click, click, click here. So this is using the line one here. Click, click, click here, and I select this area. So once I hit the back mapping, it will do the correlation analysis on this. And so here you can see it's a little bit lower. Here, if I do the, I don't know if you can see the circle very well. If I did circle here, it's even lower, so there's not much correlation if I use those pixels. And what it's doing here is whatever I've selected here, it's showing the pixels that I've selected. So it can give you an idea of where things are coming from and what's important. So for my sample, this is a soil sample. So not so exciting all the time, but for other samples, it might be more important to see where they're coming from. And then if you wanted to change the axis, you can click on axis here. You can change the so if you didn't like that 256, so if you knew what your real value was, you'd have to divide it by 256, and you can get the calibration factor here, and it will change the 256 to your values for the X and the Y. You normally click on this to show here, and then you can draw the X, Y scale. Here you can also, so then whatever, if you've changed this, when you go to export data, it will remember that, and that's the export data that it will export. The color scale, you can go, if you didn't like the, you can go change these to the real numbers if you wanted to use the real numbers, whatever you calculate here. And you can export it to another program, the data. And so I normally export it and do it in Origin. I can make it nicer and do different things with it. What change access to real values? Yeah, so you can change that. Okay, you can go click around there. Oh, and I think that's it. Yeah, I thought I'd be done half hour. Okay, so did Jan want to give an example or of axis or what do people want? I guess you could tell us what you want. We're not here for another half hour.
Yeah, that's right. If you have any particular interest on some functions or some, basically I covered many just very basics of access. If you already know how to do image single spectrum or even single stacks, then maybe we can skip those parts. And any particular interest?
I guess you have to turn on your mic if you want to
speak.
Speak, because we can't hear you. We can make everyone active, I guess, if we want.
Hi, can you hear?
Yeah, we can hear. That's Wassy?
Yes, exactly. Yeah. Can we do an example for PCA? Because I think the stuff before that was easy to follow. If we can sort of go on and do an example of the second part that you talked about, that would be helpful.
Like do the PCA analysis?
Yeah. Any simple example? Yeah.
I think just use the data. I put your data set there.
Yeah. So if we just open Axis, I'll just use the Axis one without the color, or whichever one you find.
Screen stop. Okay. So we're gonna share the screen. This screen, right? Huh? Yeah. That's our screen. Yeah, that's right. So so you're gonna load PCA GUI?
PCA.
Yeah.
Okay. Well, use which you want the PCA GUI, right? This one.
Yeah.
Yeah, that's all right.
Yeah. No, this one's the color, anyways.
Yeah. Okay. Then just follow the file.
Right. So the file, you're gonna read it in. I'm gonna go here. I'm going to read in my
transmission stack. Yeah.
Transmission stack, align,
yeah.
The align stack. I'm going to read that in. Then I'm going to go. Now this becomes active. I'm going to go find the
I0?
I0, this is my I0. It saves as XAS file. That's what it's looking for. And this was done in the stack analyzed. Okay, it brings it up, says if it looks okay. I've had sometimes where it won't display it and stuff, and so I've had to restart my computer. But generally, if it looks okay, you say dismiss. There's no other option. Now, if you want it to go in and pre-process, you could go in and clip the energy. So maybe I want to change this to 580 or something. 1580. Okay, you can change that. So now this is where it's going to show to use instead of using the whole thing. If I like it, I say do it. And then when I'm done, I say dismiss. Okay, so now I've changed that. So now I'm going to go to components. Calculate components. It's already told me. I know, but normally, I think when I do that pre-processing, it changes things. If I don't do that pre-processing here, it already determines that there are 90 here. But for some reason, when I do that pre-processing, it looks like it loses that function. But anyways, it doesn't matter. So now I know when I didn't pre-process, I got 90 here. So now it wants me to save this. So now I can save this. So it's going to save this, and I can go later in and skip the loading stuff. It allows me to load this information. So open sometimes in access means save. if you haven't realized that. Okay, so now you can go click here and see the difference in spectra and see where they're from. So you can determine whether they're noise. So this fourth one here looks like noise. Well, maybe there's something there. See here it's something here. This is noise in my spectra, but it looks like maybe component 5 is actually something here because I'm picking out the ones that I'm looking for. So you can go click through all these and see whether they're noise. And if you thought one was good, you could move it up or down. You can keep moving this one up if you want and stuff. Okay, it's actually showing it here that it's moving it. If you want, you can move it down. Now, if you wanted to save these things, nothing here become active here until you move this. As soon as you move that, you can save some. You can save these spectra as NC values. These you could read in Access if you save these. So if you're happy here, what you do here doesn't affect the cluster analysis because cluster analysis is going to allow us to look at all the components. So now just to get to the cluster analysis screen, you're going to click on this. So here you can see the spectra. This is the eigenvalues and component numbers. This looks like one that I've moved up. You can see where it's down. So here we can just say dismiss. Now it gets us back to this screen here. We're just going to go into clusters. Here, the default is, it remembers 10 here, but you can change this again and use whatever you want. Number to seek. Here I'm going to do I'll say 6 or 5. Here, this is the default. This is the one that's not using the ratio of the spectra. It's using just the differences. We now move to the angle. Once you click on the angle here, this becomes active here. Now you can choose whatever you want here. I'm not sure I found that 0.2 worked here, but feel free to play with that. Try just this case. We'll maybe try 0.5 or something just to be different. And if you're happy with that, then you're going to dismiss it. And then now you're going to tell it to calculate. So now here you can explore these two things if you want to do difference, but the angle is what the recommended way to do it now is. Then I'm just going to tell it to calculate. Tells it to calculate. It shows here the color. So the blue one is normally is using the I0. There is a little bit of spectra in the I0. In my case, here, but it's 0.02, which is small compared to the rest. If I plot all the spectra here, you can see that it's small. It's probably due to the way our sample was prepared. It dissolved in water and put onto the silicon nitride, so you actually get some dissolution of your soil. But it's small, and even though I am registering it, you can click here now to see what the clusters look like here. Okay, here I am picking up this peak here, but it's in combination with these other ones. I'm not getting the one that I expect here. So here I'm going to go to 10, what I've done before, and calculate. So I haven't saved anything yet. And so if I tell it to show all the spectra here, this still isn't doing here. Maybe doing clusters found. Maybe doing that pre-processing changed something here that I'm not able to get the cluster I want here. And then I can't. Then here you can go see the weighings. You can change the values here if you want to. And you can see which one you're on. Click back and forth. And these colors correspond to the same colors here. If you use one axis, you don't get the color, so you don't know which one is which. You can and then you can go in and save. So normally I would go in and save the whichever ones I want. So if I was going to do 20, I would save the 20. And you actually want to go save clusters to go play with these. You can read those into Axis again, or save this to clusters. This is the one you want. You want to save to clusters. You can read those ROIs into Axis again using the. It'll be the read images, and then there'll be an ROI one there. You can go read in. Okay, and then once you're happy, you've saved what you wanted. You can dismiss here. You can go now into this target spectra. You can add the ones that I never saved any, but anyways, these are ones that I saved before. If I go in and read, I can't remember why it's 2. Open it. You give it some name that means something to you, and go add another target spectrum, whichever. I think it was 16, but it doesn't matter. 16. No. Anyways, it doesn't matter. You go find the ones that you want. You can tell it to generate maps using the raw spectra. So let's generate maps here using this is from the raw data. And component 1, let's look at component 2. Okay, this is component 2. Oh yeah, okay, so I did grab one here. I use the spectra here. I know it does change it a little bit. Maybe I can't see it in this one. Maybe you go here. I can't see it, but I know that it did change it a little bit once. It just made it less, picked out less of the particles. So you can play around with these things. Then you can save these PNG maps. I didn't like the PNG maps loading into Axis. I didn't find it was as nice as the AXS maps. But go and save plots and coefficients. Save plots is this. I've never done that. And again, if you wanted to, you can normalize these spectrum using this. You can see the significant components. You can see the weights of every component. Okay, I think that's it for actually using it. Is there something else that somebody wants?
Yeah, can you hear me?
Yeah.
Yeah, so when Jian was presenting specifically about Axis, I was curious to see an example about how you go about generating a mask. And specifically, he mentioned something about using that mask to get a cleaner background. So my interest is for some of these samples that have noisy backgrounds, where PCA sometimes picks up a lot of noise. Can a mask be generated in order to help with that?
Okay. Yeah. Good question. So maybe I just close this. So okay. So we will be. I'm opening Access 2000. So what I'm going to do is from the aligned stacks. So read stacks, analyze stack process. So let me load NCNT. So nitrogen stack for the nitrogen stack. So what I'm going to load is the optical density image. So aligned OD. So open. So because it's already aligned, you don't need to read the aligned file. So it's basically no. You can. This is just a zooming factor. So if it's just a default number, so you see something like this. If you increase the number like to 2 or 3, that the image will be bigger. So anyway, so normally we study from aligned optical density stack. So you make a play movie, so you can see it's pretty aligned. So the most important is a stack, average stack. This is very important. So click average stack. So basically to average all the image in the stack, then we place this average image in buffer number 1. So this is. So you can also give a chance. This also gives Spectrum also give a chance to save the image. So typically we just use the same name of the stack name and give a AVG, which is the average image. So we can click open, means overwrite. So this is the image, average stack of all the image average. So here there's an axis. You can click. So you want to see the size or some information, just click axis. But it's not a refresh. In order to refresh this image, you need to click this buffer again. So you see there's X and Y. After the axis are being collected, refresh it, you get it. Now, we want to get a mask from this image. So basically, to get a good mask, you need a high quality image. A high quality image means you average some part of the stack, or average the whole part of the whole stack, give you a high quality image. From this image, you can generate mask. Is a image generator mask using a threshold histogram. This will be sufficient. So now it automatically give you a selection, but this selection may not be satisfied. So you need to change the lower limit. So in order to do the best selection, if I just want to select a particular region like this, then you select this region. So, but in this case, I want to select everything. I want to select the whole everything, all the image. I select as much as possible. So something like this. Maybe. So in this case, you don't need to change the upper limit, because the upper limit means the higher intensity. So if you change this, you're gonna lose some information. So basically, the upper limit you don't have to change.
You move the upper limit with the right hand mouse and the lower limit with the left hand.
Yeah, that's two. Yeah, it's over here. So lower left button, lower limit, right button, upper limit. So with the adjustment of the lower and higher upper limit, you can select most region you want. But again, still those masks need to be manually treated sometimes later. So anyway, let's get this image done. That we're gonna save mask or save image. Both you can save our regional interest. So let's save this. This is a regional interest. So basically is AOD. So it's OD. It's all. It's everything. So say open. So that's a stack.
If you use the same mask, you can put it in access.
Okay, now we have a mask. The mask basically you need a template in order to show the mask. So if you read the mask over here, it won't work. So if I read a mask, read the image, a region of interest from the actual 2000 stack, it's same idea, it's just mask. So if I just read this mask, I just save the mask. It doesn't give. It will ask you a template image. The template image you can load the average stack. So that's a mask. So this mask basically the white region is 1, the black region is 0. So this is just like so with this mask you can do many things. Just like I can use this mask to multiply a image like this image. If you want mask this mask, so this click the image, then do image multiply buffer, like multiply buffers. Then you're gonna choose a mask number 2. Scale normally is 1. So you can tell after multiplication the background is removed, but the previous image are already very good, so that you don't see much difference. But the definitely the background is completely 0. So you can copy buffer to here. So that's a multiplication of an image by the mask give you a background clean the image. So you see very clean. So same idea, we do stacks. We can use a stack to mask to modify this mask. So you do stacks, analyze again, open the mask, typically the AOD mask. You don't, maybe this time we'll give 2, so you see a bigger. So you see the noise, right? You see the noise. Then again, we're gonna do the mask. Apply the mask by process. Select the no, it's yeah. I think you need to select command. If you load the mask direct over here, you're gonna get the spectrum. So if I load mask over here, you will only get a spectrum of the region. So I'm gonna reset. I'm gonna because we want to clean the stack, so you have to do some mathematic process. So it's select command. So what are we gonna do is multiplication. Multiply by image. Yeah. Yep. But we don't save the mask image. Make sure we save the image first. So that's actually over here. So here you have to save the image. Save the image first. Write this image out. Yeah. This is the image. This is different from mask. Mask actually doesn't have template. For the image, they have everything included. So save this image. Anyway, you need because when we trying to multiply the stack by a region of interest file, it doesn't show over here. So that gives you option only the image. So you click image, it will load. So it doesn't show the region of interest. So you have to use the mask image. So this is the mask image. It basically 0 and 1. So then you do open. So it weight by 1. So now you see the stack is masked by the image. Yeah. And when you play, you only have the masked region. Finally, you want to save this masked image just by give a name like OD. For example, if you want to mask, sometimes we use like a T, clean, anyway, mask is stack. So to save this stack, you need to do sys stack NCB. So keep all the columns and rows. Okay, so now the stack is saved. You can see the stack is This is mask stack. This is just saved. You see just a process. Okay, you can open it. You can close this one now. So to view the mask stack, analyze stack process. This is the one we just saved. So open. No alignment file, and give 2. Now the same stack. Okay. Same thing you can do for the let's do a transmission stack. So stack process A. Read alignment file, no. Give 2. So we're gonna mark the times image. Anyway, the same idea. Oh, this is that'll be trouble. I think yeah, it is the inverse. So this okay, yeah, when you analyze this into because this is 0, that may be some issue for the following PCA analysis. Yeah. Okay.
Yeah, I think we already answered his concern. We won't alter too much. This one doesn't.
But there are definitely ways.
If you take the spectrum, what's the spectrum? Is it upside down?
Spectrum?
Yeah.
That's right now is transmission.
Yeah.
It's now it's still transmission, but if you select the reading in the black region, it's just 0. It's just 0, so it's hard to normalize. You're not able to normalize.
No, if you have a spectrum to read though, I0 spectrum.
Okay, I0 spectrum. Yes, I do have file. Where is the I0? Oh no, why I don't have? Oh, it's different format. It's different.
Yeah, XAS.
Yeah, XAS format.
There it is.
It's a fail because this is 0. When you're trying to ratio 0, it's infinity, and yeah, you can okay. There are for sure there are ways you can think about it. Basically, you want to replace the background by a constant. Maybe not a constant. A constant is also not good. You replace by some I0 spectrum.
Yeah.
So in that case, you probably need to do something like you can. I haven't done this before. You could try to think about the stack can also multiply by a spectrum, by a constant, by something, but it doesn't remove the noise. So
no.
Well, we can think about, yeah, we can think about how to that's exactly we want. So when you practice and you gain experience, you have some good tips, ideas, share with each other. So yeah, we all benefit. Yeah.
Is there anything else you want us to show? Don't be afraid to ask. Anybody else want us to do something?
So I'll just comment again on the math. So that was really helpful. Yeah. So I guess eventually, if I can figure out how to do it in transmission, then in some cases where the inhomogeneities are so small, when you have a noisy sample, PCA picks up all of these like noise essentially just coming from the background from your substrate. So if I could apply a mask in transmission and therefore allow PCA to run its analysis with that mask applied, then that would help the PCA. That's my theory, at least. But so I'll play around with that. But that's kind of the motivation for using the mask.
Maybe I just add on some additional information. For the mask generation, typically you involve the image modification. For example, if I just want this cube, what you can do is to do the image, doing some kind of delete. No, not delete. Delete region. So what you can do is you can do if you just want this part of tube, you can just click. Right, there are many ways you can do done and replace by 0. So then, okay, you got this image, you copy, place on another. So you see there are many ways you can do. Then you can do a subtraction between these two masks. Things you can do the image, whatever mathematically works. So you can add the buffer. Buffer number 5 by -1, right? By -1. So you see, I do a subtraction between these two images. I copy to over here. So this is the region you're interested. So then you do a generate mask again. So image generate mask threshold histogram.
But just do the minimum.
Yeah, it's just because it's just 0 and 1. You just save.
Okay.
Yeah, just save LI. So this maybe this not it's just a tip. Okay, then you open the stacks again. We don't want this one. We just use this stack 2. So then you can load the region of interest file, the tip tube. So you see only this region is loaded. So what I mean is you can modify your mask. You can do whatever operation on your mask, and finally get your design mask. The design mask can be applied to the stacks to get a spectrum.
I do a lot of component maps. Component maps. You want to to verify that the spectra that you used as your reference, you can actually pick out from your sample.
Thank you. That was helpful.
Anything else? We have the room for another 10 minutes or so. Or maybe longer, but.
Okay.
So just, I guess I'll go in again if nobody else is asking. So you said whenever you generate the 1 nanometer spectrum, by doing a stack bit, essentially you can just get the entire profile of the thickness of the sample, right? So your intensity will correspond to nanometers in thickness?
Yeah.
Okay.
Yes. Yep.
Okay, so you want to show the process?
No, I know how. I just wanted to verify that stack bit, what you're seeing essentially is sort of like a map of thickness.
Yeah, basically the stack feed and SVD feed is a linear combination. Linear combination is 2D linear combination for all the stack pixel. Each pixel is actually a spectrum. For all the stack pixels, linear combination feed. So the feeding result is a thickness. Is just each component thickness.
Okay.
Now, yeah.
The last question that I'll have is how do you go about processing tomography data on Axis or Mantis, where's a good starting point for tomography?
Okay. So for the tomography data, those basically first you have raw data, right? You have raw data. For each raw data means you have at each angle you will have a stack. Okay.
Right.
At each angle you will have a stack. So you will do alignment. You will do alignment. You will compile a stack. So for each angle.
So for the alignment, do you use Axis or do you use like BG or ImageJ?
So typically we are using, I'm using Zimba. Zimba is Zimba has a good feature. Is not like a stack analyze. Each time stack analyze to save the alignment information back into the stack. So that information is actually missing. So using Zimba, when you do alignment of each alignment, you will have the alignment information saved in a separate file, and that separate file can be applied to other stacks.
Okay.
Yeah.
So Zimba is the one that we use to analyze tomography.
Yeah. So in principle, for each angle. No, but it's okay. We still have yeah. So anyway, then after the alignment of the stack alignment, I think you will be using the Mantis. The Mantis has a function tomography. You can do alignment.
Okay.
But basically you need to align angle stack. You need to align the angle stack of actually Adam Hitchcock has some tomography data analysis information we can share later.
Okay, thank you.